All right, welcome back, everyone. So we finished all of Chapter 3 last time. We got about halfway through 4.1 last time as well. We also pointed out and reminded ourselves that our Test 3 on Chapter 3, excluding 3.6, was going to be starting today, Wednesday the 2nd, and it will end Friday the 4th. So you have 3 days, which is different than usual, and that was because we had to do that last section, the class before arguably testing on it. So I just wanted to give you a little, as much of an extension as I possibly could. So again, Test 3 is live in my math lab currently. I believe it's 15 questions, 2 hours, as I promised. Some of those questions are a little longer, so I wanted to do a few less questions. Some of them have multiple parts per usual. You still have to show your work and submit it. I am 99% confident I made the submission live in Canvas. You have to submit that within 15 minutes. Please remember you are allowed a calculator for this test. However, don't use the calculator to do everything. I reserve the right to look at your answers in my math lab, compare it to your work. And if I don't see work, I can take away all the credit. And I mainly would do that for something like graphing. Like if I ask you to graph a polynomial and you don't show me the end behavior and the intercepts and a bunch of different details like that. So please understand what you are responsible for. I'm not just going to give you a pass for letting your calculator do the work. I will be looking at everyone's work. But still, please do still email me and say, hey, Mr. Beckner, I think I just had a typo on number 14, 17 wouldn't be possible. Or, I have a small error, check my work. I think I had everything right except for this one step, and then I can get you 4 out of 5 points, or whatever the equivalent is for 15, like 6 out of 7 points potentially. But yeah, case-by-case basis on that. Also want to point out that our final exam is going to be Monday the 14th. So before we continue on, our final exam is cumulative. It will cover everything from the first day of class up until wherever we finish, is going to be Monday only, and that's December 14th. So it'll be live at 12 a.m., 12:01 a.m., whatever you want to call it. It will be due by 11:59 p.m. It'll be 2 hours. It will be in the ballpark of 25 questions, 20 to 25 questions. I'm still working on that. You will get your usual review available in my math lab that you can play around with. That will be similar to the test itself. It'll give you a clue as to what to study more specifically. You will still have to submit your work. You are allowed a calculator for this one. But this is 1 day only, and I can't make any exceptions to that. It has to be 1 day only. So please understand that you have to take your final on Monday the 14th. We will have no class that day or the 16th. So what is that, the 9th? Yeah, Wednesday the 9th would be our last day that I will actually hold a lecture. And then on the 14th, you just take your test at your convenience, maybe during our class time, maybe in the afternoon, maybe in the morning, whenever you like. And then that will be it. All right, so if you have any questions, email me. And let's continue where we left off. So we started talking about exponential functions, which the core idea, which if this was a quantitative reasoning class, I would focus on this aspect way, way more than all of the intensive algebra / pre-calc that we'll be doing. Because we think about, in quantitative reasoning, we try and think of things in as simple of a concept, but in pre-calc, we're going to calc. Quantitative reasoning students aren't going to be doing calculus, so we have to approach it from a completely different perspective. However, the perspective of a quantitative reasoning student is very, very awesome in what we can achieve with just this basic idea that it's a constant percent growth without having to get into all the intensive algebra. And I usually apply that more directly to finances, because I really, really like talking about finance with people, because I think it's something we don't talk about enough and that Americans have problems with. But anyways, can't do that right in here. So we talked about how to actually go through the graph. So we introduced the graph by doing 7 or 8 points. And then we said, well, we don't want to do this every time, especially because there's going to be subtle changes. We'll have addition or subtractions of numbers, or extra multipliers, or negatives in places. So we just want to more, that picture got a little goofed up in the process because of me hitting enter, but you can see that in last class on the YouTube video. So we said these are just the basic shapes that we memorize. When we have a base that's bigger than 1, we call it exponential growth because it's flat on the left and it explodes on the right. Now when that explosion happens, could take a little time depending on the values. It's very dependent on that. And then when your base is between 0 and 1, because we said the base can't be 1 and it can't be negative, then we have what we call exponential decay, where we're losing a percentage every year, every month, every day, whatever the scenario might be, which is why we never actually go to 0. If you just keep losing 10% of something, you never go to 0. You might have 0.000001 at some point, but then you lose 10% and that still doesn't give you 0. And the last thing we talked about was their domains and ranges, just a real quick, easy thing. And you don't have to memorize that. You can see that based on the graph. It goes left and right forever. And it only goes up forever. It stops at 0, but it doesn't include 0 because of what we call the asymptote. And I know we didn't really get into drawing asymptotes, the graph's asymptotes, too much last chapter. We did see that idea introduced when we graphed 1 over x and 1 over x squared. And we did talk about how to find asymptotes for that type of function. But just know that they're related. But for exponentials, it's only on one side. It's just a flattening out. An asymptote is kind of like a gravity well. It pulls it towards as you get closer and closer, but without actually ever touching it. So like a gravity well, but not exactly like. That's why we use the term like. All right, so let's move on to what we call transformations of graphs. And as I said, for this last chapter, we need to pick up the pace. We've got time to make up. So I'm using some notes that I already have written down instead of writing them fresh, because that saves me probably 10 to 15 minutes. And I know you might feel rushed every now and then in writing, but remember, you can always go back to the YouTube video and pause and catch up. So I hope that enables you to get everything. And I am going to get as much of this chapter completed as possible over our next 3 classes. We may not finish it, but we'll get as far as possible. And then I'll say, well, here's the file with the rest of the notes, just in case you need it for the future. All right, so transformations, exactly the same as back in chapter 2. So I mentioned back in chapter 2 that was never going away, you know, my redundancies. And hey, here this proves I wasn't a liar. These work exactly the same. So any number or sign that's outside the core of the function is a vertical change, which is why if you have your exponential and then you add the number or subtract the number, that shifts it up or down. As well as if you have the negative outside of the core of the function, that makes it a vertical reflection. Again, all vertical changes are outside the core. All horizontal changes are inside the core. So, sorry, I'm moving my glass of water so I don't knock it over my laptop. So if you have your number being added or subtracted inside the core, which for an exponential function, that means it's in the exponent, that's a horizontal shift of left or right. And please remember that the horizontal shifts are backwards. So, well, it's a good thing that I'm not using my pen. Oh, yes, it is. It is working. It wasn't working at first. There we go. It's being really wacky. I might need to write 1 or 2 things, so I'm going to unplug and replug it while I'm talking. So again, horizontal shifts are backwards. So if you see a plus, that means left. And if you see a minus, that means that it goes right. And there we go. And then we have our horizontal reflection is a negative paired with the x inside the core. Again, inside, inside, inside versus outside, outside, outside. Vertical outside, horizontal inside. And I've spent like 10 minutes trying to make these graphs work a little nicer without showing you everything all at once before class, but I could not get the erase feature to work perfectly with an undo. I need to find a way to make this work better, but I don't want to waste more time. So pretend we're not seeing things for a second. Avert thine eyes. There we go. Now, the one last thing I want to point out before we get to the example is that when you are shifting your graph, we said that back in chapter 2, we were always shifting the point that was the origin, but now these exponentials don't go through the origin, they went through the point 0, 1. So that's the point that you'll be moving up, left, right, or down. But also you have that horizontal asymptote, and if you have to move things up or down, then that asymptote is going to change. So please make sure you're considering the asymptote when shifting. You don't have to shift the asymptote left or right because it's basically an infinitely long line moving left and right. So if you move it left or if you move it right, it doesn't even matter. It's still there. But that infinitely long horizontal line will noticeably change if you have to move it up or down. So make sure we're considering that. We will see that in the examples. All right. So example 2A, we're going to graph, and we're not going to graph by using 6, 7, 20 points. We're going to graph 1 point. We're going to graph an asymptote and then make our basic shape from there. For y equals 2x plus 3. Y equals 2 to the x plus 3. So the 2 right here tells us that we're going to have exponential growth. So exponential growth, oh shoot, I can't do that. I keep forgetting I can't do it that way. Exponential growth is the one that looks like this. That's growth. Decay looks like that. Poorly drawn, but you get the idea. All right, so we are on exponential growth. So this core function, here's what I can do. Here would be the point 0, 1. You would have that flattening out on the left side, and then you would have growth on the right side. So that's what it would basically look like, except this plus 3 is here, which means we need to take this graph and we have to shift it up, left, down, or right 3. Well, since that's outside the core, that means it's vertical, and the vertical changes are direct, which means we will be shifting that up 3. So we're going to take the graph that I had in red, but we're going to move it up 3. Now, when you see the image I'm about to uncover, I will have the original one as a dotted image in one color, and then the vertical shift of up 3 as another color and as solid so that you can tell it's the answer. But you'll notice that I also have the asymptotes drawn. So here's the original asymptote. Let me do it in a different color for emphasis. So there's the asymptote of this one. And again, you can draw it all the way across if you like. When I do this by hand, though, for emphasis, I only put it on one side because it only flattens out on one side. But again, when you do it digitally, you generally see the thing going across the whole length. So then we just move this up 3. So it's this point right here, this 0, 1, that needs to move up 3. So it doesn't move up to a height of 3, it moves up to a height of 4, because 1 plus 3 is 4. And we also have to move the asymptote. That is going to have to shift up 3. That starts at a height of 0, so when you move that up 3, that does become a height of 3. Click, 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 clack, 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 clack. So here is your final graph. So the blue dotted image was the one you actually saw me draw on that other document. And you can see its original asymptote here. But then we move all of that up 3. So all we really have to do is take this point and move it up 1, 2, 3. Microsoft encountered a problem. Yay. Whatever. And then you take the asymptote, this thing right here, and you shift it up 3. So 1, 2, 3. Why did that change to a highlighter? I'm telling you, Word is wacky sometimes. I really wish there was just like a pure math program I could use to type in and have everything nice where it actually corrected my handwriting on a computer and not a tablet. So again, the blue is the image that some of you might not feel the need to draw. And if you don't, you don't. And then the red is the actual answer. And I drew the asymptote all the way across just because, again, I'm going to kind of mix this up. Sometimes I'll draw it like a computer would. Sometimes I'll draw it like I would by hand. You'll be using computers to do your answers, which is why I want to show you both ways. And that's it. You don't have to do 17 points. You don't have to do any deeper analysis. That's it. I do like to label the horizontal asymptote. Remember, asymptotes are always equations, which means they're x equals a number or y equals a number. Horizontal means it's y equals a number. Just these little bits of memorization or logic that you need to remember. And I'm showing a little bit too much. There we go. So for B, we've got f of x, and it doesn't matter if it's y equals or f of x equals, they're the same thing essentially. 4 to the x plus 2. oh, well, this base is 4 instead of 2, so that completely changes the game, right? No, it doesn't. It's bigger than 1, it's exponential growth. So we're just going to draw this same shape again. Again, poorly drawn there because it's just a quick sketch. And then it's just this plus 2 will mean it's going to shift left, right, up, or down 2. That plus 2 is inside the core, which means it's a horizontal change, and horizontal changes are backwards, so it's left 2, not right 2. So we would take our original image that has the 0, 1 point, growth on the left, flattening out on the right, and we're just going to move everything left 2. So this point right here, you would have to move left 1, 2 to over here, and it would become a negative 2, and then you just draw the same image from there. See, the horizontal asymptote isn't really going to shift anywhere because it's a horizontal change and it's an infinitely long line. In A, we had to move the asymptote. In B, we don't. Now again, in my final answer, I'll have these as solid and dotted so that you can distinguish them between what we started with and what we ended with. And there we go. So the blue one you can see here is what I drew at first, and I even labeled it this time. That's 4 to the x. And so that's without the plus 2 up there. It's without considering the change. And then we just take that point at 0, 1, we move it left 2. We grow from that on the right, we flatten out on the left. We see that the asymptote did not change at all. It takes, it's a little, the flattening out doesn't happen at exactly the same pace because everything is moved left 2, which is why it's not just going to immediately connect to that or anything. But that's it. There's nothing super complicated to this. It's just a matter of having the shape memorized and understanding why it looks like that is awesome as well. And then remembering how to shift things, remembering how to reflect things, because that's about to happen. Spoiler alerts, if you didn't already see it on the screen. Proceed. Now, you can't really tell based on the graphs I drew before I go into C, but B does grow quicker. B, in fact, will double twice as fast because the base tells you after every time you increment x1, how much it goes up. So with a base of 2, that says it's doubling each time. With a base of 4, it says it's quadrupling each time. So if the first is 1, the next will be 4, then 16, then 64, and you can see these numbers get ridiculously big, ridiculously quick. All right, -3 to the x, -3 to the x. Now, first of all, yes, this is still an exponential function because the base is not negative. That negative is not part of the base. So you're going to see something you shouldn't see for a second, but actually, no, you won't. I'm going to do it this way. I'm just going to cover up that answer for a second. So that's -3 to the x. This is not the same thing as -3 to the x. This base is negative because the negative is part of the exponent. This base is positive because that negative is not part of the base. It's just in front of it. What the negative in the first one is a reflection. This right here, we won't even see in this course. I'm not saying you can't see it in the real world. I'm just saying we don't see it in this course. And it's not a traditional exponential function. And I showed you very quickly what it would look like last time, but don't focus on that. All right. So there is no shifts in this. There's no extra pluses or minuses anywhere. So that means we just have this negative, which is a reflection. That negative is outside the core, which means it's a vertical reflection. Vertical reflection, another way to say that, is about the x-axis. In other words, the x-axis is the mirror. So if you want to see me do this really quickly, here's your original image that would start at 0, 1 with growth on the left, decay, I'm sorry, I said that backwards. Decay on the left, growth on the right, because the base itself being 3 is bigger than 1, so it's not exponential decay, it's growth. But then we're going to reflect this, which means that everything on the top goes to the bottom. So this point at 0, 1 goes to 0, -1, and then it's just a mirror image from there. So instead of growing up, we grow down. That's still technically growth, it's just negative growth. And then we flatten out on the left, and the asymptote would not change. If the asymptote is the axis, you're mirroring on the axis, so it doesn't change. So the black would be the starting problem, the red, excuse me, the black would be the problem without the negative, the red would be the problem with the negative. So there we go. So in this, it's the blue dotted one is without the negative, that's 3 raised to the x. The red one is actually the negative 3 raised to the x. Now, I would like to remind you that when you have all sorts of reflections and all sorts of shifts, that the order you do these things does matter. And I said that while there are a whole bunch of different orders that'll get the job done, this was the particular order I emphasized. I said that for the horizontals, the shift has to come before the reflection, and for the verticals, the reflection has to come before the shift. I also said that I like to do the horizontals before the verticals, and the shifts are first and last. That language paired together always worked for me, but you do whatever works for you. All right. Now, admittedly, I'm not going to do any problems on the test where it's like 3 or 4 or 5 different changes. You see all 4 of the shifts and both of the reflections. I'm not going to do that for exponentials, spoiler alerts. But I could certainly do 2 or 3 of them. And that would be enough to where you have to remember that the order matters. How can you check these things to make sure it's right? Well, you could use your calculator and you could graph it that way and see if what you did by hand matches that. And remember, I need to see work. I would love to see these shifting details. That would be excellent. You can also plug in a number into the function and see if it spits out what you expect. So if this point is here at 0, -1, that means you should plug in 0 and see if you get -1. If this point was at, say, 2, 5, you should plug in 2 and see if you get 5. It doesn't guarantee that everything's pointing in the right direction, but it at least guarantees that you shifted and reflected that singular point correctly. It is helpful. Checking your work can be helpful. All right. So to close out this section, we're going to talk about the natural number e, the natural base e. E is very similar to pi. So it's not a variable, it's a number. E is very, and I mean very similar to pi. Pi is 3.141592 blah, 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 blah. Goes on forever and ever. It's what we call an irrational number, which means the decimal doesn't terminate or repeat. And it's about 3. And pi heavily relates to circles. It comes up when you talk about the ratio of the area to the circumference. Well, the number e relates to something that is seen in finance and the natural world all over. So we said that exponential growth is constant percent change. And when you talk about finance, usually we're talking about over a day or a week or a month or a year. But in the real world, nature doesn't think about something over a day or over a week or over a month or over a year when we talk about this change aspect. Nature is thinking 10 billion times in the snap of a finger. That was me snapping my finger if you didn't catch that. So in that little snap of a finger, nature has thought 10 bajillion times. It's not even a countable number. It's infinitely many times. And when you take this constant percent change from, say, a yearly basis to a monthly basis to a daily basis to a every minute to a every second to a every billionth of a second to 10 quintillion times in the snap of a finger, in calculus you kind of learn that it involves this number e. It's just magically this limit idea turns into this e number, which is about 2.71828. Now e, like pi, is irrational. It's not just 2.71828. Hence the approximation symbol. It's 2718281827 blah 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 blah. And you might think there's a pattern there, but that pattern goes away really, really quickly. It is an irrational number, so it goes on forever without a pattern. So it's like e because it's about 3. It comes up in nature, which you can argue circles are in nature. They definitely are. And what it leads to is, well, we have two different compound interest formulas. Admittedly, I'm not going to test you on this, so you don't have to memorize these formulas, but you will see these further in your mathematical careers. You will see compound interest in times per year and continuously in a calculus course. If this is a quantitative reasoning course, we would actually be heavily focusing on this one right here, but not so much the continuous because, again, I tend to do my quantitative reasoning stuff more related to finance, and in finance, nothing grows continuously. It grows daily at best. So just some letter associations. A is what we typically call a future value. P, the principal, is the starting value. R is the annual interest rate. When you do this in, that is the number of times that you grow per year. So R divided by N is the interest rate per month or per day or per whatever is related to the problem. So like if you gain 12% per year, but you actually compound monthly, you'd gain 1% a month because 12% divided by 12 months is 1%. The exponent in T is the number of times that you compound total. So if you compound annually for 5 years, the exponent would be 5 because you'd gain money 5 times. If you gain money monthly for 5 years, the exponent ends up being 60 because you gain money every month, and there's 60 months in 5 years, aka 12 times 5. Excuse me. And I have an example that I would love to do if we weren't about a class and a half, maybe even 2 classes behind at this point because of the teaching format and missing a day. But I am going to kill that example because we need to focus on the stuff that we will be using over and over and the stuff that you'll see in your calculus courses way more than this. But I still like to talk about it. So what happens when you take this into infinity, when you, instead of compound yearly, instead of compounding monthly, instead of compounding daily, instead of compounding every hour, every second, when you compound 10 billion times in the snap of a finger, and I really hope that's not too loud, everything turns into this. You have this magical E number instead of 1 plus R over N, so that's your new base. The exponent is no longer NT, it's RT. So essentially what they're saying is this 1 plus R over N raised to the N becomes E to the R. That is what this is saying. Again, as you start compounding infinitely many times, this right here, by calculus, turns into this thing, this magical E number that's just seen all over in nature, raised to the exponential, I'm sorry, raised to the annual rate. I don't know why I said exponential. All right. PERT, also really easy formula to remember, just a terrible shampoo full of chemicals that'll probably make you go bald eventually. I'm being sarcastic. But PERT, it's pertinent. All right, so that's 4.1. And I want to just hide that for a second. 4.2. So 4.1 will be due in a week. By the way, I did get all our homework dates for 3.5 and 3.7 appropriate, if I hadn't before. I think those two are due on the 7th. That sounds right. Yeah, that's right. But I would suggest having those homeworks due before you take your test because it's going to help you take your test. All right. Logarithmic functions. I mentioned this term in passing right at the very start of 4.1. In the world of math, inverses are extremely important. Without inverses, we can't unravel things. Addition is the inverse of subtraction. Without subtraction, if you have an equation involving an addition, you can't solve for your x because you have to subtract to undo the addition. So addition and subtraction are inverses. We tend to call them opposites, but inverses is the more blanket word for it. Multiplication and division are inverses. They're also known as reciprocals of each other. We don't call them opposites. They're reciprocals, but again, a more blanket term would be inverses, because if you have an equation of multiplication, you need division to undo it. Square roots and squares, essentially, plus or minuses are involved sometimes, are inverses, because one undoes the other. If you saw an equation with a square root, you squared both sides. If you saw an equation with just something squared, you took a square root, but also a plus or minus because loss of sign generality. So they undo each other. Inverses are necessary. Well, here's the thing. While it's very easy to develop this exponential process at a base level, its inverse is not easy to develop at a basic level. In fact, it's pretty much impossible. So what some mathematician decided to do hundreds of years ago is say, forget it, I'm going to invent it. I'm going to make it up. And for whatever reason, I'm going to call it a logarithm. I am not a wordsmith. I don't actually know the word of logarithm, except for the fact that a rhythm, arithmetic, you can see where that part comes from. But the log part just means inverse of exponential. So log means the inverse of exponential. So in other words, in the same way that adding and subtracting cancel, in the same way that multiplying and dividing cancel, in the same way that square roots and squares cancel, exponents and logs cancel. So if you have a log of an exponential, they cancel. If you have an exponential of a log, they cancel under appropriate conditions that we'll go over. So again, this is something that some mathematician just said, I'm going to call it this. I'm inventing it on the spot. This is the inverse. And exponential functions are one-to-one. If you just pull up a graph real quick, just imagine you only have the black one. I'll erase the red one. This is one-to-one because I can draw, well, first of all, it's a function. It passes the vertical line test, thankfully. But I can draw infinitely many horizontal lines, and each of these only touch the function once. So it's one-to-one. That's another topic we're dusting off from chapter 2 that I said would never go away. So exponential functions are one-to-one. So an inverse exists. So crazy mathematician of the past says, I'm going to call it a log. And they just say, all right, logarithms are the inverse of exponentials. So this is the notation. F of x equals, or y equals, and this is the way you say it. There's two different ways. Log base b of x, or log of x base b. So the b is what we call the base. And yes, there's a reason we call it a base, because exponentials have bases. It's literally the same base in exponential form. And then x is just your argument, your input variable. So log base b of x is the inverse of b to the x. So these two things, if you remember, would be mirror images across the line y equals x. We said inverse functions are mirrors of each other, but not horizontally, not vertically, and not even horizontally and vertically. It's a mirror across the line y equals x. So, and we'll see this in a bit, but I just want to go ahead and point it out. If this is your b to the x, now I'm obviously assuming that b is bigger than 1 here. Here would be your line y equals x, which is our mirror. And then if you mirror that over, you end up going from 0, to 1 to 1, 0. And you end up seeing slow growth on the left. That is not an asymptote. On the right, excuse me, I said that incorrectly. Slow growth on the right, this is not an asymptote. This does grow up forever and ever and ever. It's just very, very slow because it's the opposite of quick growth. It's slow growth. And then the horizontal asymptote becomes a vertical asymptote. See that dotted line, there we go. So this would be y equals log base b of x. They're mirror images across that. So I'm kind of jumping the gun here, but I wanted to go ahead and point that out. Now, while ultimately we will be doing these inversions, we will go from one to the other once we get to equations. We're not going to focus on that aspect yet. We're going to kind of build up steam. Now, what is the point of this? And that's why you have this over here. we're trying to solve equations. If you have an equation with an exponent, so 2 to the x equals 17, and I say to solve this for x, what in the heck do you do? Because if you had 2 plus x, you would subtract 2 on both sides, because that would be the inverse of adding 2. This is 2 to the x, so we've got to get rid of this 2. We've got to get this x out from being an exponent into being down here somewhere. And that's what I kept talking about earlier. We need its inverse, which this mathematician said, all right, well, let's create it to make that happen. And in order to solve this, you'll need those logarithm things. But for now, we have no idea how to solve this. There are special cases. If this said 2 to the x equals 16, or 2 to the x equals 8, or 2 to the x equals 4, we could actually just guess the answer by using some logic and reasoning. But 2 to the x equals 17, there is no logic and reasoning to that. Because if you had 2 to the x equals 8, you're just thinking about what exponent, 2 to what exponent is 8? Well, it's 3, because 2 to the third is 8. Again, you can just pull that out of your brain using numbers. But you can't figure out what number the exponent would be to get a 17 because it's something like 3.1 blah, 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 or 3.2 blah, blah, blah. You'll never guess it. And there's no direct algebra without this stuff to do it. But again, this is our goal. For now, though, let's just focus on the aspect of converting from one to the other. So a lot of the times you'll have something in a logarithmic form, and it won't make sense, so you need to convert it to exponential form. And then other times you'll have something in exponential form, and it won't make sense, or you can't figure out the answer, so you have to convert it to log form. And in math, it's usually the grass is greener. And what that means is usually what you have is not what you want. If I give you an exponential, you probably want a log. If I give you a log, you probably want an exponential. So I'm about to reveal a formula that is extremely important that you must memorize. And this is how we go from one to the other. So I'm not saying with this little two-sided arrow, I'm not saying these are inverses of each other. I'm not saying these are inverses of each other. I'm saying they are the same thing. This relationship on the left in the box is the exact same relationship as what's on the right in that box. So again, these are not inverses of each other because this y is here by itself and then the y is the exponent, whereas both of these things above, f of x is y. So that's like y equals and y equals. This right here is like we had an inverse but forgot to swap the variables. So to convert between logs and exponentials, the logarithmic form is on the left. Y equals log base b of x. And you'll have numbers in these. They won't all three be numbers necessarily. It's usually 2 out of the 3 between y, b, and x are numbers, but not always. So that is literally the same thing as having b to the y equals x. Now, I remember the first time I saw this, I went, how am I supposed to memorize this? There's x's and y's all over the place. Good grief. Just imagine I did a Charlie Brown scream. I'm not going to pierce your ears with that. So what helps to memorize? Because as you know, I like things that help me memorize things because I'm not that great at memorization. I'm better with logic and reasoning. So the base in one form, so we call the little number that's a little lower, we call that the base of the log. It's also the base of the exponential. I hope you all know what a base of an exponential is. Base, what I highlighted, exponent, the y in that case. So the base of the log is the base of the exponent. Exponential. I think I just valley girled there for a second. Totally. Okay, so what else is helpful to remember? And this one, I tell you what, is awesome. The thing that's by itself in one form cannot be by itself again. Those two details fill in everything. The base of one is the base of the other. That's easy. Base of one is the base of the other. Then I pair that with what's alone in one form cannot be alone in the other form. So this is the alone thing on that one. It's not alone in the other. Or this is the thing that's alone in that form, and it's not alone in the other form. Those two little details, which I'm now revealing in text, that's how I memorized everything. And I've seen some people do Madden drawings where they'll go, you just take this thing and you raise it to this thing, and then you set it equal to this thing. I've seen that, but that only really works from going from log to exponential. It feels a lot more complicated to remember going exponential to log. So the red ink, I'm telling you what, has saved so many people in the memorization. Base in one is the same as the other, and the number by itself is not by itself in the other. And I said, or the variable by itself, because they may not be a number, it could be a variable. All right. So you know what we're going to do is we're going to try this out. We're going to try it out many times. We're going to get used to this conversion process. And we're going to not reveal everything. You know what? Let's just make a new one. There we go. So we'll do that. We'll do this. There we go. So a little more room on the screen. So example one, we will convert, and these will all be converting from logs to exponentials. And then example two, we'll go the other way. We'll convert from exponentials to logs. So we have 2 equals log base 5 of x. So let's pretend like this is the end of the chapter, and this is an equation, and I ask you to solve for x. Well, what is x? You clearly can't tell. First of all, you have no idea how to operate with logarithms besides converting one to the other at this point. You have no idea what these numbers mean. And honestly, most students do calculus don't have a real idea of what logs mean when they see something like log base 5 of 2 or log base 17 of 1,000,000. But your calculator would know, and you could put in a calculator via one way or another. All right, so again, let's focus on the actual aspect of converting. The base in one is the same as the other. So the base here, between the 2, the 5, and the x is the 5. That's the base. So the base of the log is the base of the exponential. So it should be 5 raised to something. And then the thing by itself in one form is not the thing by itself in the other form. The 2 is by itself in this form, which means that 2 cannot be by itself again. So I can't say this is 5 to the x equals 2. That would be wrong, because this 2 is by itself, and it can't be by itself in both forms, which means the x and the 2 are swapped. It has to be 5 to the 2 equals x. And that's exactly what it is. 5 to the 2 equals x. So the 2 is by itself before, now it's not. The x is by itself in this form, and up here it's not. The base of the log is the base of the exponential. Now, this might be throwing you off. You're going, Mr. Beckner, that answer is 25. Come on, what are you doing to me? All I said was convert, and I bet you in my math lab, if it says convert, this is what it actually wants. If you wrote 25 equals x, it might mark it wrong. Now, in a test, if you did that, I would go back and you pointed it out to me. I can give you full credit for it, which we will not have a test on just chapter 4, but you will see it in the final exam, FYI. So again, be prepared to shoot me emails for something like that. I'm pretty sure my math lab would want the 5 squared, even though it's 25. So you'll see me point out, yes, that means that x equals 25, which means, holy cow, we just solved an equation that we don't even understand. Now we know that 2 is equal to log base 5 of 25. So log base 5 of 25 is 2. What does that mean? Don't worry about that for now. All right, b. 3 equals log base b of 64. So now my variable is down here. Maybe we'll be able to figure out what b is, maybe not, but the point is just to convert for now. So the base is the same. So if that log has a base of b, the exponential should have a base of b. So it's b raised to something. The 3 is by itself in this form, which means it cannot be by itself again. So it won't be b to the 64 equals 3, it's going to be b cubed equals 64. Again, the 3 is by itself in this form, so it can't be by itself in this form. The 64 is by itself in the answer, so it can't be by itself in the question. The base of the log is the base of the exponential. And there we go, there's our conversion. So 3 equals log base b of 64 is the same thing as saying b cubed equals 64. Now, I didn't ask you to solve this. However, with some intuition, you could figure out what b is. And I don't even mean to say intuition, with some algebra. Intuition works as well, but some algebra. If you had x cubed equals 64, you know how to solve that. You take a cube root of both sides. So I didn't ask you to do this, but I'm just pointing out some extra information. If you were curious what b is, because these numbers are nice and aligned, you can take a cube root of both sides, no plus or minus needed because that's odd, and that tells you that b is 4. So 4 cubed is 64. What that means is log base 4 of 64 is equal to 3. These logarithms, I said, are really, really slow growing, and I feel like these two examples demonstrate that. When your x is 25 here, the answer is 2. When your x is 64 here, the answer is 3. Now that does pair with the bases being a 4 and a 5, but still you can see that these are very, very slow growing, which is quite contrary to exponentials, which are fast growing. That's how inverses work. If a regular function grows fast, its inverse grows slow. All right, finally, C, log base 3 of 13. Log base 3 of 13 is equal to y. I could have had y equals log base 3 of 13. It doesn't matter which thing is on which side, but I wanted you to see it both ways. So the base of one is the base of the other. So 3 will be the base. It'll be 3 to the something equals something. Question is it 3 to the 13 or is it 3 to the y? Well, the thing by itself in this version can't be by itself again, so it can't be 3 to the 13 because that would make the y by itself again. It's 3 to the y equals 13. Now this equation right here is kind of similar to this 2 to the x equals 17 that for now we have no idea how to solve it, and that's okay. So that's what I like about these three examples I introduce. A and B, you can actually make sense of when you convert it. C, you actually can't. And in fact, after you're done with this course, after you're done with this chapter, I would never want anyone to convert this. In fact, this is just to practice converting, but this right here is actually an answer because it says y equals log base 3 of 13 is a number that by doing something you can put it in your calculator. I'll have to teach you that later because traditional calculators can only handle logs with bases of 10 and with bases of, spoiler alerts, e. But there is a way to make them handle this. So again, this is an analytic answer that's highlighted. Converting it actually doesn't do anything for us. But the point wasn't to make sense of things, it was just to practice the conversions. So I wanted to see an example where the unknown was the inside, the base, and the outside. All right. So let's try a couple more. That's 375. How are we on time? 25 minutes. Convert b squared is equal to 8. Oh, I'm showing the answer. I thought I had that hidden. What happened? Spoilers. Oh, it's down there. That's why. All right, you didn't see that. Everybody had their eyes closed. Earmuffs. Eye muffs. B squared equals 81. So this is another problem because of the numbers, because of the symmetry, and I don't mean symmetry graphing wise, I just mean numerical symmetry. You could probably figure out what B is. And if you say 9, you're wrong. It's plus or minus 9 because you'd have to take the plus or minus square root of both sides to figure that out. And I bet most of you forgot about the plus or minus. And I don't mean that in a mean way, it's just what happens at our level. And I point these out so that hopefully, ultimately, you remember it. So b squared equals 81. Yes, we could figure out that b is either 9 or negative 9. But I asked you to convert this to logarithmic form, so that's what we're doing. So the base in this form is the base of the log. So it should be something like log base b. That could have been a number, but it's just a b. Now there'll be an argument and a thing by itself. So the 81 is by itself here, which means it can't be by itself again. So I can't do this, that would be wrong. The 81, therefore, must be the argument, and the 2 is what goes by itself. Another way that some people memorize things is the two things that are paired together in one form are not paired together in the other form. I've had students figure that out on their own and say that that's how they memorized it. And that's fine. Do whatever works for you. So that should be the answer. 2 equals log base b of 81. Now, did that actually help us? Honestly, no. That does not do anything constructively, but the point was just to practice converting. All right, 7 to the x equals 100. If this was 10 to the x equals 100, then you could very easily figure out that your x is 2, because 10 squared is 100. But this is 7 to the x equals 100. There's no nice even whole number. It doesn't have to be even. That's not what I meant by even. It could be odd. There's no pretty number. There's no whole number that 7 raised to a power gives you 100, because 7 squared is 49, and 7 cubed is certainly not 100. It's much bigger than that. So converting this one would actually benefit us. So the base in one form is the base of the other. So this will be a log base 7 of something. The 100 is by itself here, so it can't be by itself again. So you can't do this. That would be wrong. That means that the 100 has to be the argument, and the x has to be by itself, and that is exactly the answer. Now again, while you may have no idea what this number is in your brain, this is computational, computatable. It's computable. That would be a much easier way of saying that, Rodney. Computable. Now, again, I have to teach you a trick to put that in your calculator, but with that trick, we can now figure out what that number is. And it's somewhere in the ballpark of, I don't know, 2.5. I don't want to show you, because they have to show you the trick. 2.4 approximately raised to the, to the nearest 10th. So I was close. So that's about 2.4 if you put in a calculator. But a lot of the times in calculus, you don't have calculators. This would be the analytic answer. You wouldn't actually need to understand the size of it. You would just need it. Now, if you're doing an application or you're in a job and your boss wants the number, then you've got to know how to put that in the calculator. So that's the conversion process. It is extremely important. We will use one of these conversions much more than the other because of things that come up later. But it is still important to understand how to go both ways, because while we use one more than the other, I didn't say we never use the other. It just means we use one more than the other. All right, so when we introduce adding and subtracting and multiplying and dividing, we have to introduce the ideas of their opposites or reciprocals, as well as their identities. So those are some properties of numbers, properties of addition, properties of multiplication. While we're not necessarily going to introduce the exact same properties, we will still introduce some identities, inverses, and whatnot. So here are the 4 essential properties of logs. These are not the only properties. In fact, the next section is literally titled More Logarithmic Properties. Or if it doesn't have the word more, I think, no, it doesn't. My rant is always, it should be called More Properties, because we introduced 4 properties in the previous section. So here are 4 properties of logs. 2 of which I've already talked about before, although I didn't say what the answer was. Log base b of b equals 1. I didn't talk about, well, the ones I talked about were on the right. Log base b of b equals 1. So this says if the inside matches your base, the answer is 1. Did I show the proofs here? Yes, I did. Okay. So I will show most, if not all, these proofs as we scroll down, but let's talk about them and write them first. So when the base matches the inside, the whole thing's 1. Why? We'll see in a minute. All right, well, what if the argument is 1 instead, log base b of 1, or log of 1 base b, however you like to say it? That means the whole thing is 0. Huh? Why? Don't worry, we'll get to the why. So when the inside and the base match, the answer is 1. When the inside's a 1, no matter what the base is, that's what this bottom left one says. When the inside's a 1, it doesn't matter if the base is 3 or 1,000,000 or negative 70,000. Even though we generally don't use negative bases, it could still work. And the whole thing is 0. So these are kind of like your identities. Identities under multiplication and division is 1, under addition and subtraction it's 0. So it's interesting that we can actually pick up both of those, quote, identities. These formulas on the right, these properties on the right, are our inverse properties, where if we take the log of an exponential or the exponential of a log, as long as the bases match, that's important. As long as the bases match, the base of the log and the base of the exponential, base of the log, base of the exponential. I said that backwards for the second one. Base of the log, base of the exponential. Essentially what happens here is all of this stuff just cancels each other out. It's like adding and subtracting the same number, or it's like multiplying and dividing the same number. And the answer is just the original argument. The argument being just your input. So when you add and subtract the same number, you get 0. When you multiply and divide the same number, you get 1. When you take the square root and square of the same thing, you get the inside. When you take the log of an exponential, you get the inside. When you take the exponential of a log, you get the inside. All 4 things I said are all the exact same relationship, just from simple to complex. And by complex, I mean complicated, not literally complex numbers. So again, the ones on the right are your inverse properties. The ones on the left are more like your identities, but it feels like there's 2 identities. So how do these work? Well, let's prove and the way we prove these, is convert them to exponential form. Now, some mathematician that came up with this had to do much more than what we have to do because they couldn't work backwards. They didn't have the answer. We have the answer, and we're just going to work backwards to get the question, essentially. So if we take log base b of b equals 1, if we convert that to exponential form, we take the base, which is the red b, that will be the base of the exponential, so it would be red b raised to something. The thing that's by itself can't be by itself again, so the 1 here can't be by itself, which makes it the exponent. So that's why we get b to the first. Sorry about that scrolling issue. Ugh, come on. I'm not going to do that again. This is the problem I was having before, and I forgot. It would be really awesome if I could just erase in one fell swoop and it only did that in one erase button click or undo button, but what are you going to do? So again, the red B here is the red B, the black one is the black one, the black B is the black B. This is extremely obvious, I hope. Anything raised to the first power is itself. So some mathematician somehow figured out that they take this, convert it to exponential form, and they get an identity. All right, so that's the proof of the first one, because it makes sense in the exponential form. The second one, when we do this, again, I'm going to skip the erasing because you saw the problem. Log base b of 1 equals 0. Let's convert it to exponential form. So this will be b, the black b, raised to something equals something else. So do we raise it to the 0 or the 1? Well, the 0 is by itself now, so it can't be by itself again, which means it has to be b to the 0 equals 1. So b to the 0 equals 1. Well, guess what? Anything raised to the 0 power is 1. That is an identity under exponents. So that's it. Proved. All right. Let's take the top right one, log base b of b to the x. And this, as I said, I wouldn't prove them all. I'm only going to do the top 3 because the last one is very similar to the third one. I'll let you try and figure that out. I'll tell you what to do after though, or after we finish this one. So color for emphasis, log base red b of black b to the x equals blue x. So when we convert this to exponential form, they might go, well, this already has an exponent. Isn't this exponential form? No. The log is the outside part, which makes it logarithmic form. So we take the red b, and we'll raise it to the part that's alone, because the part that's alone can't be alone again. So we take the red b, and we raise it to the blue x. So that the blue x isn't by itself again, and we set it equal to the rest of it, the black part, which is this b to the x. That literally is the left side and the right side are completely the exact same thing, just different colors, which was for emphasis. So yeah, that works. That's a proof. If you want to try the fourth one, the one I'm circling over now, this is an exponential form because this b takes over. So you'd convert it to log form. So this b, maybe you'd make it a color, would be the base of the logarithm. The thing that's by itself would be inside now because it can't be by itself. And then the exponent would be the thing that's by itself in the other form, and it would be the same as this. You would have the left side and the right side completely matching. So again, I would suggest that you use colors for that. So maybe do this. I hate when that happens. Maybe make that a red B and make this a blue X, just for emphasis, or maybe make this X blue instead. Whatever you like, it doesn't matter. But because you have two B's and two X's, color would be very helpful for your notes. So it would be this, it'd be log base red B of X equals, and then all the black ink would be on the other side, log base B of X, and you're proved, it's done. That's all it is. You have absolutely got to memorize these. They will be on your final exam. They will be littered all over calculus. They will be littered all over calculus. They will be littered all over calculus. You might forget them for a month or two or 5, but when you go back to calculus, you're going to need them. So you better dust them off. Same as we had to dust off so many techniques before this course started, like factoring and et cetera, et cetera. All right. So I want to leave these properties up on the screen as best as I can, which means I'm going to have to pull this out some. Go. So for example, 3, we're going to simplify, mainly using these properties. Oops, wrong one. All right, instructions say simplify. I got to cover the y and the f. How am I on time? 10 minutes. That's a base of 3. I know it looks a little scribbly. Log base 3 of 3. So simplify, which generally just means apply properties. So log base 3 of 3, because the base and the inside match, that's this top left property. The base and the inside match. They don't have to be b's. They can be 3s or 5s or 7s as long as those are the same numbers of the same variable. That means the whole thing is just, what does that say? 1. The answer is 1. That's it. That's all there is. Log base 3 of 3 is 1. Log base 5 of 5 is 1. Log base 7 of 7 is 1. Log base 1,000,000 of 1,000,000 is 1. How about log base 12 of 1? Well, those numbers don't match, so it's not the top left property. It's the bottom left property because the argument is 1. The inside is 1. It doesn't matter. This is a 12. I could have written 15. I could have written 7. I could have written 1.5. I could have written 1,000,000 instead of 12. The answer, no matter what, if your argument is 1, is 0. And we've rationalized why that is right here. If your argument of a log is 1, that's because in exponential form, it's the base raised to a 0 power, and anything to the 0 power is 1. So let's make it some goofier numbers. Pi raised to the log base pi of 30. So you've got logs and exponents, so clearly it's not the top left or bottom left property, it's one of these two. It's a matter of which. Now, while you're probably initially going to just blatantly memorize these, again, I say that the idea of understanding inverses is more important. You have one concept and then its inverse concept, a base raised to a base raised to a log, or a log of an exponent, one or the other. As long as the bases match, everything cancels except for the argument. The argument's the 30, so this whole thing is 30. All right, let's do another one. D. Oh yeah, I wanted to keep that up there. Da, 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 da. Log base 2 of 8. Log base 2 of 8. Well, Mr. Beckner, what are you doing to me? The bases don't match. I'm sorry, the base and the argument don't match, so it's not the top left property. The argument is not 1, so it's not the bottom left. And you did not give me a log of an exponential or of an exponential with a log. This isn't any of the properties, you terrible, terrible person. No. This is where we have to tweak things a little bit. You are correct at the moment that right now this does not look like one of those 4 properties, but we can make it look like that. So quite often, if you have something like this, what you want to try and do is make these numbers match in some way, and by match I mean write one in terms of an exponent of the other if you can, and in this case, we can. So if you can rewrite a number in exponential form, try that. So 2, you can't write 2 except 2 to the first, so that's boring, don't do that. But 8, you can write in exponential form because 8 is 2 times 2 times 2, which is 2 cubed. So that's what I mean here. Let's take the 8 and write it as 2 cubed. And the reason we do that is because now the bases match. Now, if that 8 was a 7, it wouldn't work. If it was a 10, it wouldn't work. If it was a 15, it wouldn't work. If it was a 16, it would work because that's 2 to the 4th. If it was a 30, it wouldn't work. If it was a 32, it would because 32 is 2 to the 5th. So this is a pretty common issue that you'll need to write larger numbers in terms of a smaller number raised to an exponent and hope that you can get some matching. Because now this is log base 2 of 2 cubed. That is, it's hidden just a little bit. It's log base b of b to the x. The base of the log matches the base of the exponential. So the whole thing is just equal to the exponent. Again, the idea here is that all of this stuff just cancels each other out, and the answer is the argument of 3. But you can't tell that when it's written as log base 2 of 8. So again, this is an issue that comes up every now and then. And when I say every now and then, I don't mean like 5% of the time. I mean like, I don't know, maybe 25% of the problems in this chapter, roughly 20%. But that's enough to mean you need to know it. Now again, if that said log base 2 of 9, 9 is 3 squared, but 3 doesn't match that base of 2, nothing would happen, in fact. For now, there is something we can do, but not yet. I haven't taught you that yet. All right, so let's do this again. Let's scroll down. Here we go. Log base 5 of 1/25th. And this will be the last problem of the day. You know what? We're going to do F because it's short and sweet. This one's a little longer. So log base 5 of 1/25th. This has the exact same issue as the last time. This 1/25th, you might say, oh, well, that's a 1, so the whole thing is 0. Well, no, there's a denominator, so that changes things. All right, so what do we do? 5 and 1 and 25, or 1 over 25 aren't the same. Well, let's write the 25 as 5 squared. That's still not good enough, though, because the 5 squared is in the bottom. So you have to remember that if you have a base in the bottom, you can bring it to the top. Or if you have a base in the top, you can bring it to the bottom by changing the sign of the exponent. Now, traditionally, we usually like making negative exponents positive so we can think about them. This is one of those cases where we're going to go the other way because we need the 5 in the top to say the bases match. They don't match right now. That 5 is not in the top, so it doesn't work. So let's bring that 5 to the top and side and make it a negative exponent. Now and only now does the base of the exponential inside match the base of the log. So we can say the whole thing is just equal to the exponent. Again, that top right property, which is now hidden. I can't scroll back up, unfortunately. And you get -2. Again, the idea here is that all of this cancels and the whole thing is just equal to your exponent. All right. 7 raised to the log 7 of y. Last problem of the day, I promise. This one, you don't need to do any changes. You don't need to rewrite any numbers because the base of the exponential matches the base of the log. That was the that was the bottom right property above with the highlighting, which you can see here. So the answer is just the argument. Again, these are inverses. D, E, and F, C, E, and F, we're all applying that inverse concept where an exponential of a log, as long as you can match the bases, cancel. So the 7 log 7 cancel, 7 raised to log 7 cancel, the whole thing is just y. So there are times when we can simplify things greatly. All right, so we are finished with that idea. When we come back next time, we're going to do some examples involving, what do I want to say? Common logs and natural logs. We'll apply these concepts with those, and spoilers, it's when your base is a 10 or an E, and we just have to write less things. We don't actually write the base. And then we'll move on. All right, so we have not finished 4.2, so it's not due a week from today. It'll be due a week from next class, which is actually the day of the final. And moving forward, all homeworks will be due on the day of the final, even if you don't have a full week for them, just FYI. Otherwise, it would be an issue, right? So just know that the last couple sections of Chapter 4, you're going to have to accelerate through. But for now, email me if you have any questions. Have a great weekend. We will see you on Monday. Do your test, do your test, do your test, and don't forget to submit your work. If I have anything wrong, please notify me. And by that I mean with like the Canvas submissions over to my math lab, but I double checked earlier and I think everything's right. It looked right on my end, but every now and then the student end looks different. And it's in your quiz and test section in my math lab per usual. All right, have a good one. We'll see you Monday.